Hello, good morning. Our group is Ortega and Juliana Torres.
And we are in 5th semester of bioengineering.
Today, for Electronic 2, we are going to explain the datasheet of the LM741 operation amplifier and demonstrate some practical simulators of the amplifier.
Before we dive into the technical details, let's understand why the LM741 is so important in electronics. The operational amplifier has been a fundamental component in analog circuit design for over 5 decades, making it one of the most stylish and reliable components in the electronics engineering.
The LM741 is an operational amplifier that was introduced in 1968. It quickly became industrially standard due to its remarkable stability and versatility. This operational amplifier is widely used to electronic for various applications, including signal amplification, voltage comparison, oscillator generation, and filtering.
The specifications that we are going to explain later make the LM741 suitable for many applications. In our field, this operational amplifier plays a crucial role in various medical and biological instrumentation. Let me share some specific examples.
Okay, first in electrocardiographic system, the LM741 is used to amplify the tiny electrical signal from the heart, with a typical in the range of 0.5 to 4 millivolts. The amplifier helps convert the small signal into large voltage. You can be easier measured and desired.
Another important application is in electromyography systems, where we need to measure electrical activity produced by skeletal muscle. The LM741 helps amplify these muscle signals, which are essential for diagnosing neuromuscular disorders and developing prosthesis control systems.
We're also seeing the LM741 being used to biosensors development. For example, in glucose monitoring system, it helps amplify the small current chains produced by enzymatic reactions, making it possible to accurately measure blood glucose level.
Now let's look at the pin configuration of the LM741. It comes in an 8-pin package. Pin number 1, offset node. Pin number 2, inverting input. Pin number 3, non-inverting input. Pin number 4, negative power supply. Pin number 5, offset null. Pin number 6, output. Pin number 7, positive power supply. And pin number 8, no connection.
For our practical demonstration today, we are focused on the subtractor configurator of the LM741, which are particularly useful biomedical applications.
The subtractor configuration, also known as the difference amplifier, is essential when we need to measure the difference between two voltage signals. This is especially important in biomedical instrumentation, where we often need to eliminate common node interference, such as power line noise, while amplifying the differential signal of interest.
In practice, this configuration is widely used to ECG measurements, where we need to measure the potential difference between two electrodes, while rejecting common node noise that affect both inputs' quality. The circuit can be designed to amplify only the difference between two input signals, while rejecting any voltage that is common to both inputs.
For example, in an ECG application, if one electrode picks up a 1 millivolt cardiac signal with 60 Hz noise, and another electrode picks up only the 60 Hz noise, the subtractor configuration will eliminate the common 60 Hz noise and output only amplify the cardiac signal.
Finally, we'll demonstrate the voltage follower and buffer configuration. This might be the simplest configurations, but it's extremely useful when we need to interface between circuits and different impedance without signal amplification.
For each configuration, we will be using LFS files to simulate the circuit and show you the input and output waveforms. This will help you to understand how the LM741 behaves in real-world applications. So let's start the video. The different configurations that we can set to an op-amp have the purpose to amplify a signal, and we can customize the gain using different values of resistances thanks to the relationship between input and output. The LM741's datasheet says that a large signal voltage gain we could have depending on some conditions as supply resistance or temperature could be a minimum of 50 or 25 volts under millivolts, and typically 200 volts under millivolts, as we can say in the chart. The differential gain that we are configuring can be tested in LTSpice by setting up the restoring configuration with a 0.5 volt and minus 0.5 amplitude and 20 Hz frequency sinusoidal input signal that we are going to send 1 volt of amplitude that is going to be amplified in the amount of time that we set up with the resistance. In this case, following the formula, 5 volts under volts, having an output signal with 5 volts of amplitude. Now we are going to test a bigger gain, modifying the resistance values, obtaining 1000 volts under volts. Also, to prevent oversaturation, we are going to set up inputs lower to 0.005 volts of amplitude and inverse, and we are going to put the supply power higher to plus minus 12 volts. As you can see, the output is more or less between 10 and minus 10 volts, but here's the factor that is affecting our results. Do you know, Juli, what's this about?
Oh yes, there is a parameter that you have to explain sooner, that it's offset. Meanwhile, let me continue to explain power consumption and supply current. Okay, power consumption and supply current are key parameters that determine the efficiency of the operational amplifier. Power consumption refers to the amount of energy the device dissipates during the operation, which can affect circuit temperature or system efficiency. In LM741, the typical power consumption is 50 milliwatts, but it can reach up to 85 milliwatts when operation and 15 power supply. Okay, second, the supply current, on the other hand, represents the amount of current that the amplifier draws from the supply its own operation. In this case, LM741 draws to 1.7 milliamperes, typically with a maximum of 2.8 milliamperes. This relatively low power consumption makes a suitable for general purpose systems, although it's not the best choice for the very low power device such as battery and power sensor.
When we are working with real op-amps, apart from the differential gain, that is the one that we could calculate, we have a common mode gain that comes from how much the noise of the environment is amplified by the op-amp. The relationship ratio between differential gain and common gain mode is known as common mode rejection ratio, or CMRR. We always hope that common mode gain tends to 0. In that case, CMRR should tend to infinite, so the higher the value, the better. LM741 shows a CMRR typically of 95 decibels and a minimum of 80 decibels. With conditions as a supply resistance of 10 ohms or less, that is a good value for its applications. Now, Juli is going to show you how to calculate the CMRR with LTSpice.
Okay, as Caro was telling you before, CMRR is a key parameter, the operation amplifier, that tells us how well to op-amp can reflect common mode signals with amplifying different signals. Mathematically, it's expressed as CMRR is differential gain under common mode gain. Since this value is often very large, we express it in decibels using the formula. CMRR is 20 per logarithm in base 10 of differential gain under common mode gain, like this. let's analyze the two simulators and see how we can extract differential gain and common mode gain. First simulator, this measuring common mode gain. In first circuit, we apply the same voltage to the both inputs. You can see that we have the single voltage source 1 volt, the other voltage 1 volt, apply identically to both terminals of the op-amp. Okay, why do we do this? Because this allows us to measure the common mode gain. If the op-amps were ideal, we will completely reject in the common mode signal. Resulting is an output of 0 volts. However, in the real op-amps, there are always a small leakage of the signal, producing a slight output voltage. That small output tells us how much the op-amps face to reject the common mode signals, giving us the value of common mode gain. Since an op-amp is designed to amplify difference between inputs, this configuration allows us to measure the different gain, which is a typical much larger than common mode gain. By checking the output of the simulator, we can determine how much the op-amp amplifies the difference between the two signals, the two input signals. Following the PSRR criteria is the power supply ratio radio. It's a key indicator of the stability of an operational amplifier, as it measures its ability to reflect power supply voltage variation of prevent from affecting the output signal. It is expressed in decibels, and higher values indicates the variability of the electrical noise. In this case of LM741, the PSRR has typical value of 86 decibels and can go up to the 96 decibels, which implies that the quiet efficiency minimizes the influence of fluctuation in the power supply. There is especially important to applications where the power supply is not completely stable, such as automotive system or switch mode power supplies. However, from what to let the electronics to have the region, it will not represent a big problem.
Now, did you remember when Juli told you about the variation that we had in the simulation of gain, right? Well, when we refer to offset, we are talking about a DC voltage that is applied to the input in the op-amp. We can see its effects on this graphic, where you are adding a DC level and the signal goes up or down depending on the case. Also, the offset is going to be amplified, so it could be problematic if we have a huge gain, because its signal is going to be oversaturated or have different values as the ones that we hope for. For example, let me show you again the graphic of the gain 1000 watts under volts. I told you that the sinusoidal wave has its peak in 10 volts and minus 10 volts, as is shown by the green graphic. Instead of this, we have a movement of 0.8676 volts. If we divide it by 1000, that is the gain, we are going to have approximately an offset of 8.67 per 10 to the minus 4. The offset of an op-amp could be represented by a DC voltage source connected in series with the input. In this case, LM741 is said to have an input offset voltage typically of 1 millivolts and a maximum of 5 millivolts. We can test it by simulating in LXSpice a buffer configuration with the input connected to the ground. With this, we should wait for the output to be 0, but the DC operating point results show 1 millivolts, that is the offset that comes with this model, same as the one of the datasheet.
Continuing with the power supply range, this is defined to the power limits in the which amplifier can operate correctly with the suffering damage or affecting the performance of the circuit. So if the output signal exceeds the power supply range, its signal will be saturated, making the output signal can never be less than the power supply range. Okay, for the LM741 operation amplifier, the recommended range is plus minus 10 volts to plus minus 15 volts, but its absolute maximum capacity is plus minus 22 volts. This means that it can be used to dual source, for example, plus 15 volts and minus 15 volts, or single source, for example, 0 volts and 30 volts. However, the signal source configuration, the output signal will be limited by the absence of the negative voltage. The ability of operate the higher voltage allows the LM741 to be useful in industrial and control application where plus minimum 15 volts supplies are commonly used.
Ideally, we know that the output could take values until it reaches the supply voltage value, but in reality, due to the impedance of the amplifier, the saturation voltage of the output transistors and the power supply voltage, the output voltage doesn't go rail to rail, having that we call an output voltage swing. In this case, for LM741, if we are having a power supply of 15 volts and minus 15 volts, depending on the supply resistance, as we can see in the chart, the output voltage swing could be a minimum of plus minus 10 or 12 volts, and typically is plus minus 13 or 14 volts. That means that the output is reduced by 1 or 2 volts respect to the power supply range.
Okay, the maximum output current of the operational amplifier indicates how much current can be delivered to the load without affecting its normal operation. In this case of the LM741, this value is 25 milliamperes. This means that if the load connected to the output of the amplifier needs more current, the LM741 will be not able to deliver completely, which can use clearance in the circuit. To understand this better, imagine that the LM741 is a pipe carrying water, like a current, to a tank load. If the tank needs a lot of water quickly, can be pipe is too small, it will be not able to the while it's fast enough. In this case, the amplifier will saturate, which means that the output signal will no longer follow the input signal correctly, and distortion will occur in the circuit. This current limit makes a LM741 not ideal to application requires larger coolings, such as motor control or amplification of high-powered audio signals.
The input voltage range is the maximum and optimal values of voltage that you should use for the input to have the op-amp working properly. In the case exposed in the datasheet, if the power supply is plus minus 15 volts, the typical input voltage range is 13 volts and the minimum is 12 volts. That means you should be 1 volt below the limit, because LM741 works well with small voltage, and using a higher value might result in damaging the internal circuit.
Okay, finally, the operating temperature of the LM741 defines the range in which can operate without affecting its electrical characteristics. The standard LM741C version operates in a range of 0 Celsius to 70 Celsius, suitable for commercial and laboratory applications. However, the LM741A version, designed for the industrial and military environment, can operate over how much wide range of the minus 55 Celsius to 125 Celsius. This capacity makes it ideal for systems of the extreme conditions, such as telecommunications equipment, automotive, aviation, and space applications. If the amplifier is used in an environment outside its specific temperature range. It may experience changes, it gain input bias and internal stability without will affect the performance.
This is everything for today. We hope you have learned a lot about this operational amplifier because it's widely used in academic projects, and sometimes the reason why your circuit is not working properly and you don't understand why is because the lack of knowledge about the electrical characteristics that we find in the datasheet.
Okay, if you learn a little, please give up your like, and we are going to continue posting videos like this, right, Caro?
Of course, Holly. See you next time. Bye bye.
Bye.